Okay, so this is going to be our sixth lecture in Z transforms, all part of Chapter 5. We're going to focus on implementation basics. How do we implement constant coefficient linear difference equations? Um, as long as we got Easter right around the corner, I thought it would also be kind of fun to make this lecture in part an Easter egg hunt. I'm going to hide 5 Easter eggs throughout the lecture. Those 5 Easter eggs will each contain a single digit. If you put those digits together in the order they're presented in the lecture, you're going to get a number, and that number will have specific or special significance to EEs. The first person who emails me the number as well as why it is significant to EE will have their chance at eternal fame and glory. So keep your eyes out and think about the significance of that number. Okay, so implementation basics. What do we want to do? We would like to be able to take a constant coefficient linear difference equation and realize it. We can utilize block structures much like we did for continuous time systems. So we're going to look at direct form 1, direct form 2, and the transposed versions of those structures, as well as parallel and series implementations. These block structures are actually probably more directly useful to discrete time systems than they were for continuous time. The reason being is that with most computing technologies, whether it's an embedded system or a computer, we can directly implement those block structures. We don't need to go through something like an op-amp circuit. So all we have to do to implement discrete time systems is get these block diagrams. They'll have the same sort of advantages and limitations and range of options available that we saw for continuous time systems as well. To start this out, I think we'll just focus on a second order system. I focus on a second order system because it's the lowest order system that still allows us to have a general pole or zero, one that could be potentially complex. For a real system, if we have a complex pole, we know it has a conjugate out there. So you would take a pole and its conjugate, combine those together, and you'd get a second order system. Anything bigger than that, these structures are easily extendable. But the second order system is the fundamental building block, especially for real systems. So let's go ahead and look at that difference equation for a general second order system. We're going to have an output variable that's y of n. To that, we're going to add some a1 times the first delay of that output variable. I'm going to do this in delay form. And then we're going to get that second term in there, or the second delay in there, a2y of n minus 2. So those are all the output dependencies. If I go on to the other side of the equation, I'm going to put in the input. So I get a b0 x of n, and I have a b1 x of n minus 1, right? And then I'm going to have a b2 x of n minus 2. That's the equation we'd like to realize. In order for us to do that, we can make a really simple change here. I'm just going to take these two delay portions of the output, bring them on the other side of the equation so that I can have an expression that is the output y of n equaling a bunch of stuff. So we can go ahead and say y of n then in this case is what? It's minus a1 y of n minus 1, and I'm going to have a minus a2 y of n minus 2. I'm going to have a plus b0 x of n. I'm going to have a plus b1 x of n minus 1. And then I'm also going to have that last term plus b2 x of n minus 2. Something along those lines. I'd like to go ahead and implement this. So what am I going to do? I'm just going to start by drawing an output path that is going to be this signal that I desire, the output of the system, y of n. That is just me writing out here this left side of the equation, y of n. What is y and n comprised of? Well, it's comprised of a lot of terms, right? It's got some delays of the output as well as the input and delays of the input, and a bunch of scaling of those terms as well as some sums. So I'm going to need some basic fundamental blocks. I'm going to need a way of delaying a signal. That's just physical memory. I'm going to need a way of scaling a particular signal by a scale factor, A or B, and then we're going to have some sort of summing nodes. So I'm going to go ahead and start on the left-hand side here and give myself that input signal x of n. And what do I know? I know x of n is going to get multiplied by some b0. So I'm going to go ahead and have x of n pass through, and it's going to get multiplied by some factor b0, and it's going to continue on. Because I know where I'm going with this, I'm going to go ahead and throw in some summing nodes as well. I'm going to try to organize these in a way that facilitates us working with the structure as we go along. So I'm just going to put some sums in there. They aren't going to make total sense just yet, but they will in a minute. So right now, what do I have? I have y of n equals x of n times b0. So what I've done is I've accounted for this first term, the first out of 5 terms that make up this output. I also know that there is this b1 x of n minus 1, so I need to be able to take this input signal, delay it by 1, and multiply it by a b1. So I'm going to go over here, grab my x of n signal, right? I'm going to drop it down and run it through some sort of a delay block. We now know a z-domain model for a delay. That's just a z to the minus 1 factor. So typical in this kind of literature and the signals and systems kind of literature, that you'll see a z to the minus 1 as representation of that delay block. It's also just physical memory in a computer. So we're going to go ahead and come out of there, and what do we get? We get that x of n minus 1, right? X of n minus 1, that's the input delayed by 1, or you could think of it was the past input value. That's the memory part, right? That's going to go forward then, and it's going to get weighted by that factor b1, and that's also going to get summed in to help us make that output. So I'm going to put a summing block in there as well. Go ahead and give myself some paths here, and I'm just going to sum that in. These are all the feed forward terms. If you remember those b's, the b terms, the ones that end up multiplying our input terms, are also the things that form the system zeros. So we are working right now at an implementation that is helping us get the zeros of our system. We also know in here that we need an x of n minus 2 terms. So if I just delay again, right, that previously delayed input, I'm going to get the input delayed by 2. So x of n minus 2, just having gone through a cascade of 2 delays, that's 2 memory locations. And I'm going to go ahead and move that forward. It's going to get multiplied by some b2, and that's going to get summed in there as well. If you begin to look at this structure here, this structure looks really, really similar to what we saw in Laplace domain, the Laplace domain direct form 1. So we just handled that b2 x of n minus 2. I know that the only thing I'm missing at this point now are the feedback terms, those things that are the output term delayed multiplied by some factors a. Those factors a, if you looked at the transfer function again, those are the coefficients of the denominator. They're the things that help us implement the poles of the system. And the first one we need in there is our output y of n delayed by 1. So I'm going to go ahead and put it in here. I'm going to have my delay block, right, coming out of that delay block. I then get the signal y of n minus 1. And it needs to get multiplied not by the coefficient a1, but by the negative of that coefficient, because we had to bring it to that other side of the equation when we were solving for yn. So I'm going to get minus of a1 in there, and then that's going to go along and get summed in as well as part of this thing that gives me the output. So me putting in this this first feedback path just helped me get this term up here, the minus a1y of n minus 1. Only one to go, that's the minus a2y of n minus 2, and we probably can get pretty easy what that thing should look like. We're going to go through another delay block. Going through that delay block gives me the output delayed by 2 then, right? And it's going to also get weighted by a coefficient. It's the negative of that coefficient in the denominator, the q polynomial, if you will, and this is minus a2, and it's just going to get summed up in there as well. So I end up getting a nice structure, right? This structure has the input and its delays, each weighted by some b's, all getting summed together, and then it has the feedback terms, the delays of the output y, getting multiplied by some factors minus a's, and then getting summed in as well. A couple of things that we might note in this, if I take a look at this particular structure, by the way, this particular structure is called the direct form 1. This is direct form 1 implementation of that difference equation. We'll just abbreviate that DF1, right? That direct form 1 implementation. It comes directly from the difference equation, right? We do know that in here that we have this whole section, right? This whole section here, and really that whole section there is what? That is the zeros of the system. It is the zeros of the system because they're related to the input in those coefficient b, right? Those are in the numerator of the transfer function. We'll come back to this transfer function dependence here in a second. We've also got this, the second part, right? And that's all about feedback and the denominator of the transfer function and the poles of the system. So we're going to get in this particular structure the poles coming second. If we think about what zeros do, zeros tend to suppress the input. It makes things smaller. Zeros have a suppressing impact on the inputs. Poles do just the opposite. They tend to amplify and cause things to get bigger. So this particular realization puts poles after the zeros. So the system wants to make things small first and then bring them up to the final value. This is much less likely to have overflow kind of issues than if we reverse that order. So just like the direct form one, when we were doing continuous time system, we got this idea that zeros are going to be leading to the poles, and that ordering tends to reduce the likelihood of overflow. And so I'll say that that's a real happy face kind of an idea. That's a good quality of this particular structure. What I will also notice in here is that if I take a look at the number of memory locations, here's a memory location. That's physical memory on my machine. I need to store the past input value. Here's another physical memory location on my machine. I need to store the input 2 times ago. There's another piece of memory over here. That's the one so I can store the last value of the output. And here's another piece of memory. That's two times ago for the output. So this particular structure requires 4 pieces of physical memory to implement, right? That 4 pieces of memory is double what the order of the system is. So the number of memory locations, needed for this particular structure, DF1, is greater than the order of the system, right? It is greater than the order of the system. We'll find out shortly that that's being overcharged. It's something that we don't have to do. So this is a non-canonical. A canonical structure is one that would make the number of memory locations minimum for a particular order system, which turns out to be the order of the system. So this is a non-canonical system, and so I'm going to say that that's not so great. Okay, this DF1, just like it was for continuous time, is a structure that is both good in some ways, and it's also bad in some ways. That goodness in these ways is because it has the zeros first followed by poles. Those zeros followed by poles are going to be something that tends to reduce overflow errors. The non-canonical nature means that we're paying too much physical memory in the overall implementation. Taking a look at this again, if we look at this guy, the B's and the A's that are used in here come directly from the transfer function. I want to remind us of the transfer function that would correspond to that difference equation. This is something that we derived before. So if I go back and I think about the transfer function, well, I need a different pen on that, so I'm going to put my different pen. The transfer function I need on this guy, h of z. What does that guy look like? That h of z was equal to, we had a b0 z squared plus some b1 z plus b2, and then we divided that by, right, and we had a z squared plus a1z plus a2. All of those coefficients, b, right, are the things that are part of those feed-forward scalars that we saw in our structure. If I go back up here in my structure, right, we've got all of those b's that are going on in there. That's the zeros of the system. Why are they the zeros? Well, because those b's and all those terms up there, that forms a polynomial in z, right, set it equal to 0. The roots of that tell you the frequencies, the values of z for which that transfer function, which is also the gain factor for an everlasting exponential, we saw that before as well, is for which that gain factor is going to be 0, right? That's suppressing, that making things smaller. The denominator in here, right, we've seen that as well. That's got all those A's in there. That was the feedback type coefficients. We saw those over here as well. So over on this side, that's the poles of the system. If you've got a frequency Z that is close to one of those poles, right, the denominator is going to go to a small number that makes the overall gain factor, that cap H, the transfer function, large. So one of the nice things about this transfer function representation as well is that if you have the transfer function written, you can just draw these structures directly, because we just read off. We put this rational function in descending powers of z, and then we just read off the coefficients b0, b1, b2, right? And we go ahead and we write that in b0, b1, b2, and we keep going. If it's bigger, just having a longer and longer delay chain. And then if I've got my denominator part, that coefficient of 1 in there, which we said was standard form, that normalized coefficient on the highest power of z, really just corresponds to us having this path up here, right, that tells us where we are getting our y of n. And then below that we get a1, a2. That all comes from, right, these coefficients a1, a2. If we had a higher order system, you would keep getting more and more terms in there, and that delay chain would just continue on. We're just doing a second order, but they're really easy to extend. So we've got direct form 1. Direct form 1, right, has zeros leading to poles. That's good. It is non-canonical, and that's not so good. So we would like to look at some different structures. We can motivate these much the same way we did for continuous time. If I take a look at this, and I'm going to try to get a different color here, so I'm going to go ahead and make this guy blue. If I look at this first part here, right, I'm going to call this 1, and then I'm going to have that feeding into another block 2, something like that. If we think about that, and I'm going to move down here again, our DF1, right, our DF1 system looks something like this. It had x of n, right, feeding into some block, and that block had everything to do about the zeros of the system. I'm going to call that block 1, right? And then that fed into another block, right, which was the poles of the system, and we called that block 2 above in blue. And that gave us our, in this particular case, our output y of n, something along those lines. What I would like to try to do here, because I know that a cascade of systems, if they're non-loading, which these are, if I have a cascade of systems, that it doesn't matter which order that cascade comes in. I could do this as xn feeding into block 1, which feeds into block 2 to give me the output y of n. Or I could sit there and take my input x of n, and I could instead feed it into block 2, right, which is my poles, and then have that feed into my block 1, which is my zeros, and then to get my output y of n. We have some idea that this isn't going to be great because it's interchanged our pole zero ordering that we liked before. This is going to make a less desirable pole zero ordering, but we will find it has other advantages. Turns out this is direct form 2 in structure, and I'm going to go ahead and draw it out. So what do we have? We have x of n, which needs to feed into what was block 2 before. If we go back up here to what block 2 looks like, it starts by going into a summing node, and we see that chain of summing nodes, and then there's these feedback loops in there, and there's just a pair of them in there. So I'm going to go back to this guy and run it into a summing node, right? So we're just interchanging order of these two blocks, and that came from another summing node down there, something like that. And we had, whoops, I don't know how we just got that guy coming up, but then we just had this thing keep going out, and what did it do? It sat there and it says, let's grab a delay by 1, and then we're going to delay again, right? And then we have these feedback paths with their gains. So here was the gain minus A1, and that got fed into this summing node. And then there was over here another gain A2 minus A2 from that summing node as well. Okay, so this portion right here, right, was the block that I labeled as 2, which has all to do about the poles of the system. We're now going to run this into block 1, so we want to throw over here block 1. So I'm going to put over here block 1, and it's going to have the zeros of the system, something along those lines. Block 1, if we go back up to it, whatever block 1 was, it was something that just went into this delay chain, right? And then it had all the feed forward coefficients going on in there. So we're going to go ahead and plug this guy in as well. So we go ahead and we feed it into block 1, which was a delay chain, so z to the minus 1, and another z to the minus 1, right? And then all the feed forward coefficients in here. We have b0, we have in here b1, and we have in here b2, something like that. And the summing of these guys, right, ends up giving me the output of that block, which we said had to be my output y of n, something along those lines. In this particular case, one of the things we could notice is that although we did the interchange here, there is something that comes out that is a little bit worth considering whether we want to keep it that way. So I'm going to just do a little note here. Whatever the value is here at this red dot, that's some signal value. We could call that v of n if we wanted to, whatever it is, right? What comes out here is vn minus 1, and guess what? So is that. That's also vn minus 1, something like that. And if I come down here on the left and I go through that second delay, that's going to be vn minus 2. But guess what? That's also over here on the right. What that tells me is that this second set of delays are completely unnecessary, right? We can get rid of those guys and just tie these things back We can just tie them back, something like that. So this interchanged order, while it messes up the pole zeros, it does save me in physical memory. It is going to become a canonical structure. Let's go ahead and clean it up a little bit, just make sure we've got it all clean. So I have in here my input x of n, right? It's going to feed into a summing block. That's going to go forward and eventually hit another summing block. Then in the middle here, we're going to go through a single now delay chain, right? That single delay chain is going to have a number of delays equal to the order of the system, in this case 2. I'm going to have my feedback paths going off to the left, right? There's a minus A1, and I'm going to have another one over here. That's going to be minus A2, and it's going to get summed back up. That's all part of the feedback. That's all part of creating the poles of the system, something along those lines. And then we're going to come over here and we're going to have our B1, and I forgot one in here. I can add it in just fine. B0, and I also have in here my B2, something along those lines. So this particular guy, right, then gives me my output Y of N. All right, so what is this guy? This one is my direct form 2. So I have direct form 2. Direct form 2 is kind of nice because what do we know? It has a canonical structure. It is canonical. Canonical. That canonical means the number of memory, right? The number of memory slots, in this case indicated by those z to the minus 1, those delay blocks, is equal to the order of the system. That's a good property of this structure. It has, though, poles leading then to zeros. It puts the poles first. Those poles first tend to make things big, and then the zeros would pull them down to their final value, but making things big first gives us an increased chance of overflow, and so that's not such a good thing. We've exchanged a structure that was a sad happy, and we've made it now a happy sad. So it's about a net balance of being equal. We would like to do better. Fortunately, there is something about these transform domain type expressions as well. So those transform domain expressions are going to, the transposed structures, I should say, the transposed structures in here are going to be the way we're going to get rid of some of that sad faces going on in here. So let's talk a little bit about transposed structures. Transposed structures. We can get transposed structures by taking any of the structures that we had before, direct form 1 or direct form 2, and applying the basic transpose process. I'm not going to prove this, I'm just going to give it. What is the 3-step process in here? 1, we're going to reverse input, and output, something like that, right? The second thing we're going to do is we're going to reverse all arrow directions. And then the third step is a compound step. In this particular case, we're going to make nodes, that should be a D. We're going to make our nodes into sums, and we're going to make our sums into nodes. If we do those 3 steps, we can turn a regular structure into its transposed equivalent. It does not change the functionality of the system, at least from a theoretical standpoint, but it can give us some other kinds of advantages. So I'm not going to do this for the transposed direct form 1. TDF1, I'm going to let you do on your own. So TDF1, you do it, right? You do it. So you go ahead and do that one. That turns out to be the sad implementation. And so that's an exercise you can work on. It's not commonly encountered, but we will do transposed direct form 2, and hopefully we'll find out that this gives us our happy. If I go back to what I had before, that's this structure. This was my direct form 2. I'm going to go ahead and cheat a little bit in this case. So I'm going to grab that entire structure that I'd previously done. I can copy that guy out. We will be able to make some quick changes to this guy as we come down here. So we'll hopefully get this guy pasted in. I'm going to move it around so we can see it a little bit. So this was direct form 2 as we had before. And I just want to start applying, and let's go ahead and do this in a color red for fun. So I'm going to do this in red. I'm going to start applying the 3-step process, and then we'll clean it up afterwards. First step was what? Exchange input and output. So X here is going to become Y, right? And Y is going to become X. That's step 1. Step number 2 is that we have to reverse all arrow directions. That actually makes some sense here. It would make no sense if Y was actually flowing away from the output. It's got to flow towards the output. So this guy's going to have to go that direction. Same thing for now the input. It's not going to flow to the input. The input's going to flow into the structure, something like that. All of these other like scale factor ones, we're going to see those guys swap direction too. So all of these guys are going to be pointing in the opposite direction that they were before. So we're going to have something like that. Things that we're going here are going to go down. This guy is going to go over, right? This one's going to go this way. This one's going to go that way. We're going to get this one coming down. These guys are going to come and meet towards the middle. Same thing here. Okay, so we've got all those reversed arrow directions. The third step was that all nodes have to become sums. Well, there's 3 nodes in this particular structure. Here's a node, so it's going to become a sum. Here's a node, that's going to become a sum. And here's a node, that's going to become a sum. And then it also said at the same time, you have to make what were previously sums into nodes. Well, this structure had 4 sums, and so we're going to go ahead and make that a node, and we're going to make that a node, and we're going to go ahead and make that a node, and we're going to go ahead and make that a node. This should be my equivalent transposed direct form 2 structure, which I'm going to clean up here and put in a more standard orientation where input is on the left and output is on the right. So if I go ahead and draw my input, x of n, that's this guy sitting over there. What does it feed into? It just feeds into a straight path here that comes down, right, and has 3 paths going forward, which each get multiplied by these various coefficients. There's the b0 in there. There is a B1 in there, and there is a B2 in there, something along those lines. Those scale factor paths then go into some summing nodes. So these guys are each going to run into a summing node, and then out of that summing node on the top, we are going to get my output, y of n. There is the feedback path from that as well that feeds back. So that's going to come down, and it's going to be entering through these coefficients, the negation of those a coefficients. So I'm going to have in here something like minus a1 and minus a2, something along those lines. What's in the middle? Well, those are our delay blocks. So we're going to have a delay block here, z to the minus 1. Z to the minus 1 is just a piece of physical memory on my PC, remember that? And then these guys are going to chain up. They're going to go through something like this. Okay, so this should be in a completely equivalent structure to what we had before. It does the same exact system difference equation. We're going to verify that here in a second. But what I'd like to note here is, what do I have? I have all the B stuff first. That is the zeros of the system, and that goes and leads into something that does the poles of the system. That pole zero ordering is good, right? Makes things small first and then brings them up to the final value. Less chance of having overflow error. We also notice here that the number of memory, right, the number of memory spaces is equal to the order, in this case 2, of the system. That is also a happy phase. That is a canonical condition. This is a canonical structure. It is a canonical structure. So this is our happy realization. Does it do what we think it should be doing? Does it really give me that same difference equation? You can't always easily tell this from some of these structures, but in this particular case, we can, even in the time domain. So let's go ahead and do it. I'm going to start, and I'm going to do this all in red just so we can follow along. I'm going to start by writing an expression for y of n. So I have y of n. What is y of n equal to? It's equal to a sum of a bunch of stuff. One of the things that gets summed in there is x of n times b0. That's this path. So I know I'm going to get an x0 times x, not x of 0, that's b of 0, right? We're going to get b of 0 times x of n. So that's one of those paths that comes in and sums, right, to give me that output y. What's another one that I get in here? I get x of n times b1. delayed by 1. So if I take a signal, multiply it by b1 and delay it, the scale factor doesn't really matter. So I'm going to still have that b1 out front, and I just take that signal x of n minus 1. So that's going to get delayed in there. Same sort of an idea. I get this path here that is x of n times b2, delayed not once, but twice before it ends up getting through. So I'm going to have a b2, right, x of n minus 2 in there. So that's a good portion of it. And then I have what? I have yn times minus a1 delayed by 1. So that's almost all of it. So here I'm going to get a minus a1 y of n minus 1. And then the very last path was yn times minus a2 delayed twice coming through there. So a minus a2 y of n minus 2. If you compare that to the previous or original difference equation we did, it's the same. So of course, we can easily verify that this particular structure, this transposed direct form 2 structure, does indeed implement this second order difference equation that I wanted. And it does it with a happy kind of realization that definitely makes me happy. So where are we at on this? We are trying to make sure that we have a full understanding of this. Let's run back through this really quick. We were starting this thing out by looking at a difference equation. That's this guy. We just wrote it directly from the equations. We got this nice structure, called it direct form 1. It had zeros followed by poles, was non-canonical, and that ended up giving us, in this particular case, a structure that was happy sad. We then interchanged the order of these two guys, trying to make something that was a canonical structure. We were able to do that. That gave us a happy sad, so we weren't fully good. We went to this transposed structure, and in this transposed structure, we just reversed input and output, reversed all arrow directions, made node sums and sums nodes, and we got a structure that was both canonical and had the proper pole zero ordering. That proper pole zero ordering, right, is definitely something that ends up giving us a structure that is going to be well behaved. It's going to be less likely to have overflow in there. So we're really happy to see that as well. In this particular case, we like that overall happy structure. So in continuation, we have now 3 structures. I left one for an exercise to you that would get the 4th one. That would be the transposed direct form 1. That would be the sad. About the only thing that we have left to really worry about at this point is taking a look at the idea of implementing things as either series or parallel implementations. To do this, I think I'm just going to take a very specific example and see if we can realize it in multiple ways. So let's see what we can do with this one. So I'm going to do as an example, and this is going to be to show. In this particular case, both, right, series and parallel realization options, options. We're gonna do that through a specific example. So let's take a look at a difference equation. The difference equation I'm going to choose is going to be y of n minus 1/4 y of n minus 2 is equal to 3x of n minus 3x of n minus 1, and I'm going to have a minus 6x of n minus 2. So this is a real system, right? It's implementable. This is in delay form. Second order system, I've got a maximum of 2 delays in there. Constant coefficient linear difference equation, causal, realizable, real system. Don't know yet whether it's stable, but certainly something that we could build. I would like to start working about thinking about getting structures to realize this system. And to do so, I'm going to take a look at this guy's transfer function. So I would like to get the transfer function of this system. That is the h of z. This is going to be easier for us to manipulate and be able to see some different options for realizations that are either series or parallel as well. Transfer function we know is what? This guy should be something like a P of Z by Q of Z. This is something we talked about in a previous lecture. If I go back to my original difference equation, I could have written this guy as what? I could have done this as like an E squared minus a quarter acting on Y of n. This is just advanced operator form being equal to what? 3E squared minus 3E minus 6 operating on X of n. This first thing here, right, was my Q. This second thing over here was my P. So I should be able to very quickly get my transfer function. That's the Z transform of the unit impulse response as well. I can get that very easy straight from the coefficients of my difference equation. Remember, the Q has all those little coefficients A that are part of my structure typically. P has all those coefficients B that are part of my structure. And we do want to make sure that that lead coefficient, right, of the E is equal to 1. Okay, so what is my h of z in this case? I'm going to get a 3z squared minus 3z minus 6 over z squared minus 1/4, something like that. Now, if I asked you in this particular case, give me the best, right? The best as far as what we've introduced, realization of this as a single stage best realization. What would you do? What is the best single stage realization? Well, we've already looked at that, right? We know the thing that makes us double happy is the transposed direct form 2 would satisfy that bill. So if I wanted to just very quickly before I get to the series and parallel realizations, think about what the direct form 2 of this particular example would be. I know it's second order, and so I'm going to get something like the following. I would have x of n feeding into some coefficients. What are these coefficients? They're like B0, B1, and B2. B0 in this case is 3, right? And then I have my B1 is being minus 3, and my B2 in this particular case is minus 6. All of those guys feed into some summing nodes, something like that. So I'm going to get all of these summing nodes coming in there like that. And I know that there's a delay element that is in the center chain here. So I'm going to get these delay elements. So canonical structure only need 2 elements for the second order system. And I've got my feed forward all my coefficients that make up the zeros of the system. Out pops y of n, so we know there's the y of n there. You'll notice that there's no z term. That means that there's going to be no path, right, that goes in that middle with a feedback. So this middle path here that I'm going to just highlight in green or put a little bit of green in there is not going to be necessary because the coefficient for z in the denominator is 0. I do have, though, that path that is connected with the minus 1/4. So my A2 in this case is minus a quarter, but I know those feedback coefficients need to be negated, so I would have a 1/4 in there. This would be one way, right? This is the transposed direct form 2 way of realizing this system. Okay, so let's look at some other ways of doing this. Let's do a series realization and let's do a parallel. Usually you wouldn't do this with a second order system already. I'm just picking a low order one so we can get through it in a timely way. But the basic strategy here is always about the same. So we had what? We had an h of z, and that h of z was equal to a 3z squared minus 3z minus 6 over, and in this particular case, we had a z squared minus 1/4. I could take this guy and factor it up. If it was a much higher order, I would factor that guy out using my favorite package, something like MATLAB, and then maybe I'd group together any kind of conjugate roots and I'd remultiply them out so that I could get little quadratic terms. For the time being, we're going to do these as first order terms just to keep life simple. The denominator in this particular case is something you can probably just root out by inspection. I know that's going to be like a z minus a half and a z plus a half. Boy, that answers our question as to whether this system is stable, right? Both of those roots are inside the unit circle. We have a root at a half and also a root at minus a half. And so with both roots inside the unit circle, this is indeed a stable system. It's going to have some basic nice behavior in there. I could pull out a constant 3 as well, and I could root out the numerator. And the numerator in this case turns out to be not too bad either. It's a z minus 2 and a z plus plus 1, something along those lines. This factored form is going to be nice because this factored form will help me get to something like a series realization on this particular structure. So this series realization just needs to be done something like what? I know that if I have systems in series, right? Some system and followed by another system in series where I have an input X and an output Y, call this first system some H1 transfer function, this other guy H2. The overall equivalent to this guy is H1 times H2, right? We'd seen that before. If you had systems in series time domain expression, you'd convolve their impulse response. When you go to the transform domain, convolution becomes multiplication, so you just multiply their transfer functions. So I can look at my h of z and I can say, can I break this up into something times something? And certainly I can do that here. Let me go ahead and in green highlight one set, right? And then I'm going to make this guy in blue and I'm going to highlight another set. I can call that one that's in green my h1, right? Something like that. And the one in blue is going to be my h2. So that would be one way of doing this as a series realization. And if I wanted to do that, I could do that with my favorite structures. Let's go ahead and do the first one. Let's call that first one 1 and the second one 2, something along those lines. Let's do the first one with direct form 1, and let's do 2 with direct form 2. You could pick whatever structures you want. That kind of highlights that there's going to be a lot of ways of realizing these systems. Furthermore, there's a ton of other things I could do. You see that coefficient 3 in there. I didn't have to put that with 1. I could have put that with 2, right? I could have matched up z plus 1 with z minus a half in the denominator, and I could have then taken that z minus 2 and matched it up with a z plus a half. There are a lot of ways that I can pair poles and zeros or put in overall scale factors or whatever the case may be. I've just chosen one of them. And then for each one of those pieces, each one of those H1, H2, whatever I'm doing in my series, there's a limitless way of realizing those with different structures. I'm going to do DF1 here and DF2. So what was my DF1 structure looking like? I knew my DF1 structure looked something like this. I had my input X of n coming in, right? And I had a delay chain. This is going to be a first order system. I did this as a series expansion. It made that second order a cascade of 2 first order systems. So I'm only going to need a first order DF1. And then there's going to be these feed forward paths, which are going to have the 2 B coefficients associated with that H1. There's going to be a summing node coming in here. That's going to feed into another summing node for which there's going to be the output of that H1. That's not my full output yet. That gets fed back through a delay, right? And it's going to get multiplied by the negative of the feedback coefficient. So if I look back at this, my B0 is going to be 3 because it's 3z in the numerator. So I'm going to get a 3 up there. My B1 is going to be 3 times minus 2 or minus 6. So I'm going to get a minus 6 on that one, right? The denominator tells me that my A1 is minus a half, but I need to negate that. So that's going to be a 1/2. So that is a direct form 1 realization of my system H1. That needs to feed into H2, which is going to be direct form 2. What does my direct form 2 look like? Well, direct form 2 ended up coming into a summing node first, and then it was this middle that went down through a chain. It was a canonical structure, so I had that z to the minus 1 coming down. My feedback came first, so I did the poles here first. That was a little bit less desirable, but okay, we're going to do it in this case. And then we had the feed forward part, so we're going to have our 2 coefficients, the B0 and B1 for that second stage, and then that guy's going to come up, get summed in, and out pops, now in this case, my total output Y of n. What are these pieces in here? If I take a look at that blue block above, right, that's the H2. My B0 and B1 are both 1. So I'm going to get a 1 here and a 1 here. You probably didn't even have to draw it as a multiply. The A1 in the denominator is a half, but that needs to be negated, so I get a minus 1/2 in here. So here's an example of taking a second order transfer function, right? If I wanted to go ahead and do that second order transfer function, let's do this in red. That second order transfer function, there it is. I wrote it as a product of 2 transfer functions, right? Lots of choices for how you group that. I picked a particular way, and then we just took the first one and cascade with the second one, something along those lines. So there's an example of, in this particular case, right, this idea of getting a series kind of relationship in there. All right, so let's work towards what would be a a parallel realization on that. I'm going to rewrite out again my h of z. My h of z in this particular case we said was what? It was a 3z squared minus 3z, and then we have a minus 6 over, we had a z squared minus 1/4. If I'm going to do a series realization, it might look something like this, right? I have some system, call it h of 1, and it's going to be in series with another system, h of 2, and I'm going to add them together, right? There might be more than 2, there could be 3, 4, there could be lots of them in there. The input is x and the output is y. What is the overall transfer function of this guy? Well, it is h1 plus h2. When you have systems in parallel, right, their transfer functions just add. So if I can re-represent this h of z as a sum of pieces, right, those pieces each individually that make up that sum could each be parts of systems that would make up this parallel realization. There's lots of ways of getting a thing like a rational function into a sum of pieces. A partial fraction expansion works that way. In this particular case, I'm not going to do a partial fraction expansion. I've already worked out the math in this case. I'm just going to give a sum of two pieces, an h1 and an h2, that work for this system. It is close to a partial fraction, but I've done a little manipulation just to make it look a little bit nice. So what do I get in here? Minus 6z minus 15/4 over z minus 1/2 plus 9z plus 33/4 over z plus 1/2. Okay, if you just wanted to have some idea, just a little bit of an idea that this might be right, if we found a common denominator here, the first term, right, this first term out here has a z minus 1 in the denominator. To make a common denominator, I'd have to multiply top and bottom by z plus 1/2. To get the other guy with a common denominator, it needs that z minus 1/2, so I'd multiply top and bottom by z minus 1/2. You go ahead and do those multiplications, and then you recombine all the numerators, and you should indeed get that original numerator, 3z squared minus 3z minus 6. Well, let's just take part of that. If I take this first term, right, and I multiplied it by a z plus 1/2 over z plus 1/2. I'm not too worried about the denominator. I would end up getting a minus 6z squared. Those are the only z squared terms. Same thing if over here I multiplied by a z minus 1/2 over a z minus 1/2. The numerator would have a 9z squared. That would be the only z squared term. Add those two together. So I have a minus 6z squared from the first one, plus 9z squared from the second one. Minus 6 plus 9 is 3. That's this 3z squared. If you keep doing that, you would find out that all the other terms come out as well. Okay, so I've represented my system now, right, as a sum of two pieces. Ignore the red. This first piece I could call my h1. The second piece I could call my h2. I would like to go ahead and realize these as well. And I'm going to go ahead and realize these. Oh, let's do it something like, let's realize h1 as a transposed direct form 2. And let's do h2 as a direct form 2. I'm picking these out of the air just so that we can get practice running these different structures. It would probably be most likely that people would pick things like the transposed direct form 2 in their typical implementations. So we would like to go ahead and try to get these as well. So I'm just going to remind myself over here as to what these different pieces are. h1 of z, which we said we were going to do as a transposed direct form 2, right, is equal to, in this case, we have a minus 6z, and then we also had a minus 15/4, and that was all over a z minus 1/2. And then we said for a direct form 2, we would do that h2 of z, which we said was equal to what? If we go back and look at that, that's at 9z plus 33/4 over z plus 1/2. So I'm going to go ahead and write that out as well. We have a 3z plus 33/4 over, in this case, z plus 1/2, something along those lines. I've drawn these one on top of one another because we are trying to do a parallel realization, right? So I'm going to have my input x of n, and it's going to feed two different systems. It's going to feed a system up here on top, right? That's going to be my H1 system, and it's also going to feed a system on the bottom. The system on top is a DF2 structure, so I should get my zeros first, right, followed by the poles. So this first one's going to come through some coefficients, right? These coefficients in here, coefficients, those are going to get into these summing nodes. You could go back up in the lecture if you wanted to see this, and then we are going to get some particular output on that, but that output also gets fed back through another coefficient, something like that. And then we have in here what? We have a delay block, something like that. And we just need to be able to get the coefficients in here. Okay, so what are the B0 and B1? B0 is -6, so I'm going to get a -6 here, and B1 is going to be a -15/4, so -15/4, something like that. And then my A1 is -1/2, and I have to negate that, so that's going to be a 1/2. So that gives me this guy. That output, right, is going to come down here, and it's going to get summed up with the output of my other system to give me Y of N, something along those lines. The second system then, we said we wanted to do is a direct form 2. This is also a canonical structure, and that canonical structure, something doesn't look right on this. What did I get wrong? That was supposed to be a 9z plus 33/4, so I miscopied that 9z plus 33/4. So let's go ahead and correct that as well. So I'm going to get rid of that 3, and we're going to make that a 9 because it was a 9z plus 33/4 over z plus 1/2. So the second structure in here, we said we were going to do as a direct form 2. That's going to do poles first, followed by zeros. So we're going to come in here and we're going to hit a summing node, right? And then it's going to go forward, and there's going to be the B1. If we take a look at this particular case, if we wanted to, let's just do the zeros part first. We're going to come in here and we are going to, in this case, it was also canonical structure, right? We know all the direct form or transposed direct form 2s are canonical structures, so I get a z to the -1. And then we are going to need that feedback term coming on in here. So this feedback term, right, is going to come back over here. And the A1 in this case was 1/2, so we have to negate that. That's going to be -1/2. Then we need our feed forward coefficients that go on in here. And so I'm going to do my feed forward coefficient. And this first feed forward coefficient has a value 9, right? And then that's going to come out into a summing node. And then we have our other feed forward coefficient. That other feed forward coefficient in this particular case is 33/4. And that gets summed up here. And the output of that comes together with the other to create my overall output, Y of N. So this is an example of taking that second order system, which happened to have all real roots, and I broke it up into a parallel realization. You can get that parallel realization in many different ways. This isn't quite a standard partial fraction expansion type approach, but partial fraction expansions would usually be a very good way of doing that. So, quick summary. What have we done? We've talked about implementations, right? Implementations on these guys. These implementations, right? We talked about were things like direct form 1. We talked about direct form 2. We talked about the transpose of all of these guys, so we could get a transposed direct form 1, and we could get a transposed direct form 2. The one that's probably the best on this guy is this guy. That's the happy one, right? This one, which we didn't actually do, but you could do on your own, was going to be the sad, and the other ones have a mix of the two. We also looked at the idea of series realizations, and we did cascade realizations, and followed it up with a couple of examples as well. So I don't know. I think that's about what we need to get through on this lecture. Next time we're going to spend more time talking about the transfer function and its connection to this idea of frequency response. So we're getting close to that idea of frequency response, and we're going to look at frequency response concepts not too much longer, and we will end up being end up being done with this chapter, with this particular chapter 5. And so we'll just end out the lecture in this particular case, and we'll see you next time.